the second item, we're asked to find the shear moment diagrams for this loaded beam where we've already been provided these two reactions. So we're not going to actually write out the integral expressions, but rather we are going to rely upon those relationships that dv dx equals q and dm dx equals v to form the basis for our work. We have a pin support, so we start off at zero shear, but immediately we have a reaction. It goes down to -10. There is no distributed load, so the slope of the shear diagram is constant until we hit a load. That's a concentrated couple. It doesn't have a direct effect on the shear diagram, so we're going to march all the way across then at zero slope, and we're still at a -10 kips of shear. Then we have a reaction that is represented here by the point load at 28. We go up to follow that to a net of positive 18, and then we pick up a distributed load acting downwards. Okay, and that area then will be -1.5 times 12, or a negative 18, and that will be a decrease that's steady, constant slope, 1.5 kips per foot, and that'll take us to zero right there. Right, so there's your shear diagram. The moment diagram follows along from our shear diagram. Start off at the zero moment, no applied couple at that location. We immediately have a negative slope though, and that's going to go over until we reach where the applied couple is located. So that area will be -60 for -10 kips times 6 feet. Likewise, this other area is going to be the same kind of thing. Might as well get all the areas while we're at it. This triangle will be 1/2 the base times the height, so that will be 1/2 of 18 times 12, or 108 kip feet. Alright, so let's get this done here. We've got 0th order curve here, so we're going to go downwards to reach then -60, and then we immediately hop up with the discontinuity by positive 12 to a net of -48. Follow the same slope as we had before because the shear is the same value, and our total change as we go over to point B will put us at the net of -108, at which point we immediately pick up positive slope, positive 18 kip feet per feet. We end up with zero slope, so tangent to the horizontal axis. We're going from a first order curve to integrate down to a second order curve, and so to get that in there, then we could get our French curve out and draw that in there like so. Has to be concave down to meet our beginning and ending slopes, and there's your shear and moment diagrams for item number 2.